like to start the session with the chair as well as the co-chair. On behalf of the organizing committee and on my personal behalf, I request Muthukumaran sir to chair the session. At the same time, I request also Dr. Ritesh Kumar to co-chair this session.
My pleasure.
It is my immense pleasure to introduce to the august delegates and all my fellow friends, Dr. K. Muthukumaran, the chair for this session. Dr. K. Muthukumaran is currently professor in civil engineering at National Institute of Technology, Tiruchirappalli, India. He obtained PhD in soil structure interaction and marine geotechnical engineering from Indian Institute of Technology, Madras. He has published more than 120 papers in international and national journals and conferences. He has completed 5 R&D, including ISRO Chandrayana 2 mission projects and more than 60 major consultancy projects in geotechnical engineering, and published 2 patents, including moon soil, a method which is a method of manufacturing of highland lunar soil simulant. He has guided 8 PhD students and 5 MS by research, and more than 40 MTech students in geotechnical and allied research areas. He is the founder chairman of Indian Geotechnical Society of the Trichy chapter. He has received DST Young Scientist Award, IGS Srimatri Indra Joshi Biennial Award and Keynote Paper Award in GeoMat conference held in 2005 at Osaka, Japan. So with this brief biodata, I welcome wholeheartedly Dr. K. Muthukumaran to chair the session. Sir, welcome, sir. It is my pleasure to introduce Dr. Ritesh Kumar, the co-chair. Presently, he is the assistant professor in earthquake department of esteemed organization, I.I.T. Roorkee. He earned his MSc Engineering and PhD in Civil Engineering from Tokyo Institute of Technology, Japan. He also earned MTech in Earthquake Engineering, the soil dynamic stream from IIT Roorkee. He was a postdoctoral researcher at REKN, Center for Computational Science in Kobe, Japan, before joining IIT Roorkee. He also worked as an assistant professor at GEU, Dehradun, and as a PhD intern at University of California, Davis, USA. Dr. Kumar does research on, but not limited to, physical and numerical related problems, dynamic soil structure interaction, and risk and reliability analysis in geotechnical earthquake engineering. He was awarded University Gold Medal for his bachelor degree. He is a recipient of the DAD Scholarship for the IIT TU9 Master Sandwich Program for Germany, and MEXT Scholarship instituted by Tokyo Technological University, Japan. So with this brief biodata, I welcome Dr. Ritesh Kumar to co-chair the session.
Thank you, sir. My pleasure.
Thank you. Now it is over to the chair and co-chair to convene the sessions. Over to you, sir.
Thank you so much. Good morning. Welcome to the technical session. I take this opportunity to thank the organizer for giving us this opportunity to share the session, and very important session. And we have a very great, eminent personality to deliver the lecture, Professor K.S. Rao. I believe all the 5 speakers are available with us. Professor Raj, I hope all are available with us. All the 5 speakers, technical speakers.
There are 3 are available, sir. Others has to join.
Okay. Okay, fine. So please, the time management, please you have to maintain according to the available speaker. So since out of 5, as of now, we have 3 speakers, so we can give enough time for the speaker, Professor K.S. Rao.
Exactly, sir.
I'm very happy to. I'm very happy and pleasure to introduce Professor. So speaker Professor Rao, receiving his Master's MTech from IIT Kanpur, and PhD from IIT Delhi. Joined the Faculty of Engineering, IIT Delhi in 1986. His academic and research spanning over 40 years has been on engineering behavior of rock mass, stability of slopes, underground structures, foundations, numerical modeling, and seismic hazardous microzonation of megacities. An established teacher, researcher, and active consultant, Professor Rao has supervised 25 PhD and more than 180 MTech theses. And currently he is guiding 14 doctoral students. He is the recipient of IGS Professor Leonard's Best Thesis Award and Diamond Jubilee Award and 20 other IGS and MIT. Professor Rao published technical papers in national and international journals and conferences. He has been the principal investigator of 20 major sponsored projects. Professor Rao designed and developed a large-scale polyaxial facilities, static and dynamic cyclic triaxial apparatus, impact and pre-testing facilities at IIT Delhi. A large-scale direct shear test facilities for mine dumping materials was established at CMPDI, Ranchi under his technical guidelines. Professor Rao is the honorary fellow of Indian Geotechnical Society and contributed extensively to the growth of IGS for more than 24 years at various capacities. Professor Rao has been the editor of IGJ, Indian Geotechnical Journal, and IGS newsletter. He was the president of Indian Geotechnical Society and president of Indian Society of Engineering Geology for the term 2011 to 12 and 2018 to 19 respectively. For his overall contribution, he was awarded the Lifetime Achiever Award in 2016. And Professor Rao delivered the 41st IGS annual lecture and received the Kukulman Award for the year 2020. Consultancy project in the area of soil, rock, and earthquake geotechnical engineering. His recent geotechnical modeling work for assessing the stability of Senab Bridge abutment has cleared the way for the national importance. He is the consultant for Rongtok, ZMOC, and Zogzilla tunnel projects. With this brief introduction about Professor Rao, it's a well-known personality. No need to have a introduction for Professor Rao. Nevertheless, for the new audience for this particular group, and as well as the customary of this program, I briefly introduced Professor Rao. Now I request Professor Rao to take over the floor. So now over to you, sir. Please.
Thank you for the nice words, say Professor Muthukumaran and Professor Govindarajulu and also Professor Ritesh. A very good morning, delegates. Thank you very much, for telling about my so-called, academic, the attributes. That's okay. So at the outset, let me thank the organizers are also for giving me this important slot, to share my views on seismic hazard assessment for tunneling. And I also thank the chair, giving, slightly extra time, and I'm desperately, looking for that because I loaded, the large number of slides. So, but nevertheless, the depending upon, your convenience, so please let me know, like, accordingly, I will try to manage it. So the title is Seismic Hazard Assessment for Tunneling, and tunneling includes, all the underground structures, which includes not only the tunnels, mines, shafts, adits, drifts, powerhouses, caverns. For the military installations, so we do a lot of underground structures, and also for the repositories of hydrocarbons, as well as for the nuclear waste repositories, and many other applications are also there. So I read, say the future is underground. So tunnels are not new to us. So since human inception, say they keep digging the earth, and for the shelter they used to do it, and then subsequently for the transport purpose, a large number of tunnels have been constructed. With the advent of explosives, that is the black powder and the dynamite, so the excavation becomes a cutting tool. So thereby, a large number of tunnels, so they have been constructed in the for the last 200 years. And these are some of the tunnels. If you see it, say the 54 kilometers length, 57 kilometers length. Also, the diameters are gradually increasing it, so with the with the time. So not only across the world, but of course, so in an Indian scenario also, large amount of tunnels are coming, be it road or the railway tunnels. So extensive tunneling is happening it of late, especially in the mountainous Himalayan region. So you might have heard about, say the Atal road tunnel. So this is almost like 8 kilometers at an altitude of the roughly, say the 3,000, say the kilometers, 3,000 meters. So it is a very prestigious, very sophisticated tunnel. So I'm closely associated with the construction of this particular tunnel and subsequently also advising it. Pir Panjal tunnel is also another tunnel. It's a railway tunnel, so the 11.15 kilometers. Then Chenani Nasri tunnel, which has been designated as Shyam Prasad Mukherjee road tunnel, and many other railways and road tunnels, they are coming up at different locations. And of late, extensive planning of tunnels for the roadways as well as railways, they are being done. Just so I divided my presentation into two parts. The first part is so that to give the tunnel scenario in the static conditions, and then subsequently I will be switching over to the under the seismic conditions. So if you see it, so because the tunneling is not a usual undergraduate, so I was, so talking about this, so the continental drift and, say the seafloor spreading. So the mid of the ocean, if you see it, say you will be seeing it, so a lot of. So the seismicity is because of, say the boundaries of, say the crustal boundaries, the plates, say the because of say the push and pull, say the lot of seismicity is there. So Himalayas, so I was showing that say the Himalayas are formed because of the push and pull, and then thereby most of the projects are actually situated here. So they are tectonically highly seismic and say the tectonically very active, and a lot of challenges are there. So they're doing the tunneling, say in the mountains. So I was sharing some of the information, so in the static condition, how do we, say the design. So the tunnel diameter versus, say the material surrounding it is important, and especially when it is rock, say the jointing patterns, etc., makes, say the whether the tunnel is actually this stable or, say the unstable. Also, the principal stress directions, their orientation is also major concern when we are doing the alignment of the tunnel. Like, so if you have the crisscrossing joints are there, so when you make the tunnel, so a lot of collapses will be taking place. So there are, so the stereographic projection, you can anticipate how the failure is going to take place. So thereby you are prepared, so to make it stable. Sometimes, so you are cutting across, so the faulted zones or the shear zones. So they also, so they gives you the differential, say the settlements. So in the soil condition, so the K0 we normally talk, say the coefficient of earth pressure, and in the rocks, so it is very positive. That means, so the ratio horizontal versus so the vertical is very high. At shallow projects, if the project is say the above 500 meters, most of our projects are actually the shallow, so thereby the horizontal stresses are very high rather than say the vertical. So thereby you need to take into account so the while planning it. If you are say the continuous say the strata, the loads are actually the transmitting, or the stress is actually the transmitting to the bottom, and you are making a tunnel. So obviously because of this say the stress cannot actually say the go through the vacuum. So thereby these say the 4 points will be more vulnerable. So squeezing will be taking place on the sideways, and here so this is on the crown, and so the invert locations, so both will be experiencing it so the tensile stresses. So both these stresses will make the tunnel very unsafe. So without spending much time say what I want to say is low stresses and high stresses, depending upon say the situation, both conditions are not good. So thereby you need to follow what is exactly the stress state available, and to suit that so your tunnel alignment should be there. Individual blocks will be sliding it. Once key block slides, so the rest of the other blocks so will be also sliding, then collapse will be there. And this is, you don't have the raw joints, but very good in situ stress conditions. But when you make say the tunnel, so you are releasing the stress, so that is actually the yielding it, and then there with the spalling and the rock bursting is going to happen. So this is the squeezing. So the rock under the high stresses will be subjected to the creep and the squeezing, and then thereby your tunnel diameter is actually the getting reduced it. So this is the best thing what one should actually do it. Once you establish this is so the vertical is actually sigma 2 and sigma 1 is so the horizontal, and your shape of the cavity is this to suit this, then it is going to be stable. And now also like major principal stress is so the vertical, or here horizontal and inclined. Accordingly, the locations where so you will be having intense stresses, so there will be the failures. Here the side walls will fail. Here the crown and the invert is going to have the problem, and here so the at the spring levels so that you will be having the situation. So material behavior is not so it's inborn. The material behavior is so the conditions. So if the material is highly brittle, and the strain softening is actually going to take place, and it could be say the elastic plastic, that is the squeezing behavior, or the material is actually exposed to the elastoplastic deformation, and then so that you have the viscoelastic so the creep behavior, so the hardening behavior. You see this so the tunnel is already there, and you have the support system, but the tunnel is actually getting squeezed, and also so the lot of water issues will be there. When you make the tunnels, the side walls so looks very perfect, but then say with passage of time so the squeezing is taking place. Here already the support system in place, but then they will get crumbled, and because of so the rock bursting, squeezing, they are very common. And sometimes so you do have when you are excavating the tunnel, the face is going to collapse. So a sugar cube type of so the highly fractured material is keep coming unlimited, and along with the water, so it's a major issue. So and also sometimes so you will be getting a lot of so the big cavities. Then also water issues so the I indicated. So what you do is how do you how do you do the analysis and design of tunnels in the static condition? Of course, investigations. We do the investigations, complete mapping, because the tunnels are actually going lengthwise, and determine so the behavior of the material, the boundary conditions, and say the excavation methodology you work out, and required support systems, and then that is how actually the tunneling is done. So geological, geotechnical, hydrological, seismological testing is extensively done. and then also, so we conduct, so the institute stress state and for planning the tunnel. If you see it, say the Terjagi way back, so the 1946, not only in soil mechanics, so his contributions exemplary for the rock mechanics as well. He put so the beginning for the evolving of rock mass classification systems. I tell you now, the rock mass classifications are invariably designated as design methods in rock engineering. He found so that when you have the tunnel, say the how the loads are going to be calculated, overburden pressure, what is actually the coming, so that say your tunnel properly can be designed. Apart from that, over the time, say that we have come up with say the active span length and its stand-up time. Let's see, like unsupported span excavation is actually done. How much time it is actually going to be stable? So these two things, so the jointly combined with say the rock mass classes, so makes the rock mass classification systems as design methods. Most renowned classification systems in the rock engineering are RMR, that is rock mass rating, and then say you have the Q system. One is given by the Barton and colleagues. The other one is say Benvisky and his colleagues. From different experiences, they evolved what are the parameters which influence the stability of the underground cavities. And then of late, so the GSA classification is also extensively used. So these classification systems are extensively used not only to classify the rock, but also design of the support systems and also to estimate the rock loads. So not going much into it, just I wanted to say that these classification systems will be useful, say that to decide about the excavation methodology, the support systems, and many other engineering, say the feats which we do it, say for the in the tunneling. So this type of charts are available depending upon the RMR or the Q value. So you can design, say the support system. Also, when you do, so you may be doing the full face excavation. That is, in one go you are doing the excavation, or sometimes if the rock conditions are bad, ground conditions are bad, so you will be going bit by bit. That is, what we call is drift support system. Analytical solutions are there for the regular shapes. And when you make the cavity, so plastic zone will form, and then beyond that you have the elastic zone will be there. If the tunnel is actually remaining in the elastic zone, so the stability is definitely there. So the plastic zone, stresses in the plastic zone, stresses in the elastic zone, and radial stresses, yield zone radius, displacements, you can get it. So analytical solutions are there. Based on that, so the one can do the design. And once you estimate the stresses and say the start excavating it, you need to get the ground response. How a particular ground is going to behave when you make a tunnel. Is it going to collapse so the fast, or is it stable enough? So this is a ground response, so the analysis curve. In the beginning of excavation, say this is the P loads are coming in the opposite direction. Support system is going to compensate that. So thereby the tunnel periphery is going to be stable. But it is not possible to put the rigid support immediately as soon as you excavate, because there are cycle times are there. So after elapsement of some time, so there will be displacement. Because of the displacement, the loads are also going to gradually reduce it. So the too early, too late, you cannot have it. So thereby ideal, say the timing and the displacement, say the at what displacement you want to restrict and put the support, that you need to decide. So there is a very clear-cut methodology is available for the design of say the tunneling. So not only the tunnels, for the stations, so we normally use the cut and cover methods. So then in the drilling in the soils, so what we use, so the EPBMs, so that is earth pressure balancing systems. So since the soil is, so they're having the earth pressure, and when you are making the tunnel, so it is going to squeeze inside. So thereby to restrict that in the opposite direction while doing the tunneling. So these TBMs, so will apply the pressure. And subsequently, of course, you will be putting the lining. Rock tunneling is tunnel boring machine. So apart from that, so you have the NATAM. So that is Norwegian tunneling technology. I will come back to that, so later. And then you see that, so this is how actually we do the cut and cover, and we do the cut and cover, so for the, not only the stations, but, so sometimes the shallow tunnels, especially the urban tunnels, we do this. And in Delhi, say the very dilapidated buildings, but still, say the 15 meters below, so you can have a nice metro. The NATAM concept is, so the earlier we used to think that, so the rock mass surrounding the tunnel is loading the system, so not contributing for this stability. But that is not really correct, since the rock is, so the harder, even if it is, say the fractured. If you restrict, say the displacement by putting a shotcrete or, say the rock bolt, so then a huge amount of strength is going to get mobilized, and that is actually going to give you the support to the tunnel. So that is the reason why, so with the least support systems, so the very gigantic underground structures are possible. For this, so the monitoring of the tunnel, which is already done, if you monitor it, so with the instrumentation, it will be good, so that, so what is really happening it after cutting the tunnel. If the response is, so there is good, then it's go ahead, or otherwise you will be changing it, say what you need to do it. So once you have the excavations, you need to have the support. What are the support system? Commonly we use it, rock bolts, because to tie the periphery to the more elastic, so the media, so that, so the compressive zone will be formed. So rock bolts, shotcrete, so a layer of, say the 1 layer, 2 layers of shotcrete of different thicknesses, we will be using it. This is pneumatically exerted, say the cement cement slurry with high, say the pressure that will be ejected, so that, so that it will form a very liner. So the wire mesh also associated to it, and lattice girders are very special type of support systems. So now if you see it, so you have the freshly cut tunnel, and you are putting the bolts because you have the plastic zone is there, and beyond that, elastic zone. So you are creating a compressive envelope, so thereby the stresses are properly distributed, and then, say tunnel periphery is stable. This is you can also put, say the shotcrete layer. So that is what the support systems normally we adapt. So here it is, so the simple shotcrete that is actually going to good enough, to be stable. So the bolts, the variety of bolts are there, and I'm not going into the details of it. So each one is, so they're having its own, so the functions very easily executable in the site, and they can be of different lengths. You do have the cable bolts also for the China, say slopes. So we have gone up to the 60 meters cable length, say the cable. So then virtually the whole slope is, so is stitched with bolts and other support systems. So thereby the slopes are stable. Sometimes, so we go for the flexible support systems, so they as well. So in certain conditions, so the ground is very poor, and soil, the rock or soil, so the conditions are very yielding. In such cases, say with a lot of water, so we do the pore pulling. So the pipes will be injected, and through that, so the grouting will be done. And a artificial canopy is created before we excavate it, because when you start excavating it, your roof is going to collapse. So thereby what you do is, so you create a canopy, and then you proceed further. In the city environment, urban tunnels, so you have the structures are there, but so the tunnels are going to be subjected to the lot of so the issues. In such cases, so the because of the overburden and the other loads, so there will be the convergence will be taking place. So the tunnel is actually made up to here, and beyond that also the convergence is actually appearing. So how do you predict, say convergence and pre-convergence? Say the loads before you really excavate. That's what say tunneling all about. Anticipate and say they try to be prepared for it, and then say they execute it. Now, a typical cross section of a tunnel, if you see it, see it's having a lot of systems. And this is the Atal tunnel. So very famous, so the Atal tunnel connecting the Manali to Spiti Valley is virtually the 9 kilometers, so the tunnel. So you have the ventilation chambers are there. So this is the main tunnel section, and below that so you have the escape tunnel, what we call is the egress tunnel. Below that so you have the drainage system is there. Whatever the water which is actually the coming, since this is a drained tunnel, so it will be sent to this main drain, and the main drain is actually going to deliver the water say through the portals. So this is how actually say the cross section looks like. If you see the tunnel, it's a beautiful, highly sophisticated, every 500 meters, so the lot of electronic surveillance, so the systems are there, escape routes are also there. This is how actually the Atal tunnel, so it looks like this. So this is the egress tunnel, which will be below. This is the escape, so the tunnel. In the static condition, that is the way, so that we do it. So now I will be very quickly, so they're going to the seismic, so the analysis and design of, so the tunnels. These are the different, say the important items I will be briefly address. As we have seen, like, say we do have the tunnels which are made, say through the cut and cover process. This is the typical, say the scenario. And you may have the bore tunnels. So this is you have the using the drilling machine, so that you are doing the TBM missions. And then you do have the immersive tunnels also. So that's below the water. So the off late you might have. You must be hearing it, say a lot of tunnels are coming connecting different islands or islands with the mainland. So through the underwater immersive tunnels are coming. So again, underground structures, so you do have the cut and cover, so that so one above the other, or so the side by side you can have it. Portal structures, as well as so the deep chambers and waste repositories. So these are the big caverns or cavities, so which are made for the storage. We know it, so the earthquake, when the shaking is actually taking place, two type of, say the effects are going to experience. One is the ground shaking, and the other one is, so the ground failure. Ground shaking, so we know that there are body waves. So the body waves are, say P and S waves, and you have the surface waves. You have the Love and Rayleigh waves. So normally we know surface waves are more damaging it than the body waves. So obviously the ground or the tunnel is actually going to get experienced, say the ground shaking. So the tunnel should be stable enough, say for these motions. Then there is, so the altogether the failure of the ground, so we experience, so the liquefaction because of the pore pressure increase, so the momentarily, and then thereby the soil behaves like a liquid, unable to sustain, say the any structure. Slope instability is a major issue. So especially the entry points. So the entry points of the tunnel are known as, say the portals. portal stability is very, very important. And if the tunnel is actually crossing the fault and the fault is very active, and normally, say they will become active because of the seismic, the shaking, then it is a major disaster, say for the tunnels. So if you see it, say sometimes a lot of subsidence, etc., is going to take place because the ground is deforming it terribly. So most of the contents are, say through this particular classical work. So the seismic design and analysis of underground structures. So it is published in Tunneling and Underground Space Technology. This is International Association of Tunneling is, say treating this as a some sort of, so a code. Any tunnel that is actually coming that should, say go through this particular the analysis, because the appropriate codes are still, because our experience of tunnels, tunnel damages, so the under seismic, so the conditions are still, so in the initial stages. So obviously the tunnel specifications are going to be very important. So the rock and the soil properties, ground motion characteristics, the depth of structures, that is what is the depth at which the tunnel is actually there, and what are the structural elements, so of the tunnel lining, and what is the geometry important. So what is the difference between the on-ground structures and underground structures? So normally what we do is inertia of the structure and the resonance are important for the design under the seismic conditions. For the underground structures, the inertia of the structure is less than the inertia of the surrounding soil. That is different here, so the inertia of the structure is, so is very high there. Here it is, so is very less than the surrounding. So there is a misguided conception exists, so due to the small structural inertia. So since inertia is very low, say the why to worry about, underground structures under the seismic, say the conditions. One need not, so the worry about it. That's the overall, say the general idea, but it is not really correct. The seismic design of underground structures is governed by the free field of the ground motion. So it is not that, say the ground and the structure combinedly you do the analysis, say the normally we do it, so that there is no structure. So for the free field, so that you will be doing it. So also one can do the soil structure, so the interaction. Seismic response of tunneling during the earthquakes show that the response of the tunnel is dominated by the surrounding ground response, not the inertial properties of, say the tunnel itself. As is been told that, say inertia is very less of the structure, but the ground. The focus of the underground seismic design, therefore, is one of the free field deformation of the ground and its interaction, so with the structure. So that's the main, so the difference, for the seismic considerations for the underground structures. In any way, whether it is a static or underground, static or dynamic, deformation management is important. When you excavate something, obviously displacement deformation is going to be there. So your excavation methodology should say manage the deformation before it really collapses. And also in the earthquake conditions, it should be stable. It's a classic study, so that has been done, to show what is the maximum acceleration, so that you will be getting it, 0.36 G here underground, and on the ground, so that it is 0.61, and whereas the structure is actually experiencing it, so on the surface very high, so the acceleration 0.78. So that thereby the damages are, so the quite evident, so the on the ground. So whereas, so the if you see it, so the inside, and then in the tunnel, if you see it, so the tunnel is actually experiencing it, so the less than the ground itself. So insignificant inertia effect, and in spite of the fact that, so the similar frequency content. Now, very of late, so the several documented cases are being available to understand, like, the earthquake damages on underground structures. So I.I.Sc, JSC, and the other researchers, so they're publishing huge amount of data of the damages that are taken place, so to the tunnels. Underground structures built, so the of course, so the 1927. This is one example, so the I was referring it. For this, so the measured free field is, so maximum is 0.25 G. So observed damages to date are insignificant, including, so the large, so the Loma Prieta earthquake. So what it means is, so the tunnel engineers are cautioning that, so they don't neglect it, the earthquake effect, because we have not really come across, so the major shaking as far as, so the underground tunnels are concerned. So this is typical, so the failures which happens, so in the underground, so the tunnels. This is the portal, so the portal is completely choked, so rolling of boulders, and then now you see that, so the tunnel is completely clogged, and then failure of, so the tunnels inside, so the forming the big cavities. These are the real examples of, so the tunnels which were damaged due to the seismic, so the events. Another classic study that is available. So the lining is completely, so the cracked. The thin lining system which is actually there supporting the tunnel, that is completely cracked. So the fallen concrete chunks, and then fallen concrete lining, so they around this one. So you get, so the shear cracks. Sometimes, so the warping or the flip of, so your invert is actually taking place, so that. And also you see this, so the cross section. So the cross section is totally, so the displaced. Hello. So this type of, so the portal failures, so the you will be getting it. So thereby the portals, so there should be stability of slopes, and to secure the portals, so is very important. And this is also another case, so the die-cast substation, so the collapse, which was actually due to the cope, so the earthquake. What are the damages, so the normally we get it, so the columns are get crushed, so the roof slab collapse, so the road surface completely settled, and the shearing of, so the bars, etc. So the central column dividing, so the both sides, so the completely crushed, and then of course, so the some damages in the wall, etc. So for the design of this particular tunnel, so the no seismic consideration is actually done. So thereby, if the designs are actually made without seismic consideration, something like this, so there may happen. So less damage than the surface structures. That is in comparison also with the surface structures and the damage. Definitely, so the less damage is felt. And damage decreases with the depth. If the deep tunnels are there, say the damages will be less. And cut and cover is, so the tunnels will be exposed to more damage. The structures in rocks are safer than the in soil. So, that is also, so the we can imagine that. And stabilization of surrounding soil is more effective than the increasing liner thickness. There is a concept that, so if the liner thickness is very thick, so it will protect, but it is not really correct. So rather the ground behind, say the lining, that should be, you should actually do, so the improvement in that. Damage may be related to the P ground acceleration and P ground, so the velocities. Trunk motion duration is also important. This is quite obvious, like, so the duration is high, so then damage is more. Slope stability is especially for the portals, so the very important. Damage of lined tunnels are less than so than the unlined. This is also quite obvious. So that is the reason why you cannot, even if the surrounding rock is good, it is, so the advisable, so that you do some amount of, so the lining. So how do you go about the whole, say the analysis and design? So first, so they establish the seismic environment, the way which we do it, so the usually seismic hazard analysis, ground response analysis, and for that, so you need to have, say the geophysical tests. So this input, so you are using it, assessment of structure behavior due to the seismic seismicity, and you can do it in also the analytical methods through the analytical methods. There are again, say the two variety of, say the analytical methods are available to us. Assume that, free field deformation. So, and then, so the other one is soil structure interaction. As I indicated earlier, that normally, say we prefer the free field deformation assessment, and then try to inbuilt, say in your structure to take into account of, say those deformations. So for this, say this is the overall, so the methodology. Soil structure interaction, so then this is for the full slip or the no slip conditions. So which is suggested by the Wang and the Pengin, and in the HASAS, so these both methods are actually is given. So seismic design, so the procedure, this is the usual stuff which we'll do it, say the conducting the seismic hazard analysis, so establishing the design criteria, and the ground motion parameters, say we evaluate, and so in for the seismic hazard, say we know they established two procedures. So you have the deterministic seismic, hazard analysis, and say probabilistic, so the hazard analysis. I don't want to go into that. So this is the studies which we have carried out, say for the Delhi region, and also we did the PHA assessment, say for the not only for the South Africa, but also, say for the Delhi and other regions, say we have done. It is a probability based. So based on this, say that you get, say the seismic hazard, and also, say that we do the ground response, so the analysis. Ground response analysis, so the two ways again, so as I indicated that, say the maximum credible earthquake, and the other one is, say the operating design, say the ODE condition, and I just, so they indicated, so the how it should be under the MDE, say the different load combinations will be there. So you have the dead loads, you have the live loads, and so the earthquake loads are actually going to be there. So for that, so there are, so the equations are available, how you consider, so the loads in the MDE. So similarly in the ODE also you will be able to, and then thereby you will be able to assess, so the ground motion parameters of a particular, so the area. So this is all actually the same effort. One important thing is, what is the mode of, say the response of the structure depending upon the shape of the structure. Let's see, like, says circular. So it will be experiencing it, the axial compression and the extension. Whereas, say if you have, say the wave is actually passing, so along the tunnel or across the tunnel, longitudinal bending is going to take place. And then whereas, say this is wobbling effect, and then, so the raking effect for a rectangular or a squarish, so the tunnels. So the main considerations are actually for this. How do you go about it to predict, say the different parameters to find the wobbling or the raking effects of the structure? So this is again, so when the waves are actually passing across the tunnel, say how you consider, say the PES wave and Rayleigh waves. So this is for the wobbling. Again, so the wobbling with a non-perforated and perforated, say the conditions, and this is for the raking. So how do you consider, say the shear strains, so the from the raking, say the motions. So similarly, soil structure interaction is also, so the highly established, so the process. So these are the equations which can actually give you the axial strain, bending strains, and the shear forces. and assuming, say certain spring constants, so you will be able to get the ground displacement and also, so the actual strains into the system. And apart from that, so for the ovaling assessment, say compressibility C and, say flexibility F ratios, so the important, and in different, say the conditions, and what is the amount of maximum thrust, say that will be possible, so that you can, and then thereby, say you can, say in soft soils, what happens in the stiff soils, what happens in the perforated ground, say how the F changes. So that is what, so the delt. Similarly, like, so the soil structure interaction, so the flexibility ratio is very important, and the F can be calculated. And then if the F is 0, the structure is rigid, and then if it is less, so the structure is, so the stiff. And of course, so there are different, so the conditions. So there are, so the certain things which are not still a lot of research is actually happening. It tunnel joints at portal and stations, so tunnel segments, connection designs, seismic retrofit, and design consideration for the structural support members, design strategies of the ground failures. So this is a major thing, though it is rarely happens, but the ground failures, so they may take place, and the seismic design of high nuclear waste repositories. So these are major. So with this, so I wanted to conclude it, so quickly in 1 minute. Knowledge is well established, so as in on-ground structures. Knowledge is not, so that means, say still a lot of scope is actually there. Measured data and studies are fewer, and state-of-art reviews are available to some extent. Seismic loading of underground structures are not as significant as commonly perceived. FFD and SSI, so they are very important consideration. In contrast, structure inertia plays, so the major role into it. Considerations for the large ground deformations are equally important. Adoption of design guidelines is not difficult and is recommendable. So whatever the guidelines which are actually there, say procedurally, they are not very time consumed. That can be handled very nicely to get, seismic effects on the stability of the. So regular, so the follow-up one should actually do it. The main research, so is lies in the one should actually do the instrumentation of the tunnel, so that when there is a earthquake, so the damage profiles can be, say properly, so that the prediction possibilities, so the one can have it open on the ground. So this is extensively that happens. Mechanism of load transfer from the overburdened soil to the ceiling of the slab, that is still not clear. Influence of high vertical accelerations on generation of large compressive loads on tunnel lining. Improved numerical models is required. Significance of ground motion directivity and the incoherence, particularly in the soft soils, is very required to be clarified. And repeated cyclic load effects are not really assessed. And non-conventional seismic joints of the lining, bolting, water insulation materials should be studied. So future is, so in underground, and we will be having, say such a beautiful environment which are safe, not only in the static conditions, so in the dynamic condition also the tunnels could be, say the safe. So these are the young budding, say the tunnel engineers from IIT Delhi. And this is the institute which I belong to. Thank you very much. And I'm very sorry that, so that I have exceeded, so the time limits.
No, sir, it's completely fine. Thank you so much for your very informative lecture. This is very perfect blend of, core and applied research and its application into practice.
Yeah.
So as of now, I can't see any questions from the audience. So because we are running a little bit behind the schedule, so I would like to start